Well, guys, it is 1 o'clock. I think I'm gonna go ahead and get started here. I'm glad to see all of you, and it's been almost 3 weeks between the spring break and then Zoom last week and then the days in between. It adds up quickly. It feels like forever. But I'm glad you guys made it back, and I hope everything went okay for you. I hope you all had a great spring break, first of all. And I also hope that last week was manageable for you. Um, my parents still have this enormous house. I don't know when they're gonna get rid of it, but whenever that is, I'll have to go for a long Zoom session. Because they got a lot of stuff to do. But I was able to help them a little bit last week, so I appreciate that. It's kind of an emergency. But everything's good now, and yeah, so we should be good from here on out to be in person, although I must have picked up some kind of a bug while I was on the plane ride back. Because I'm not feeling the greatest, that's why I got this mask on. So we'll just have to see how I'm doing by Thursday. If it's really a problem, I'll have to send you a note, we'll do something else, but hopefully it'll be okay. Let's see, I passed back the exams, unless you just came in, you didn't get your exam back, I'll give it to you during the break today. I'm not gonna go over the midterm during class. Overall, they were better than the first midterm, so that was good to see. So the average went up a little bit. People are figuring it out a little bit, how to kind of navigate the stuff. I hope that's how you're feeling about it. But if you have individual questions, or maybe you were one of the ones who didn't necessarily feel a whole lot better about the second exam, by all means, feel free to reach out to me. We can talk during my office hours. Go over anything in detail. I did put a copy of my solutions into the resources folder. So you can always put your exam side by side with that, kind of see how things shake out. Of course, there's sometimes more than one way to do things, more than one way to think about things. So if you want to have those kind of conversations with me, we certainly could do it. I just don't want to do it during class time. So that's it with the exam. In Canvas, you should have your updated grade as of now. Keep in mind, it's not exactly accurate because ultimately I'm going to be upweighting the best part of your grade so that will count an extra 5% weight in your overall grade calculation. I'm going to take 5% away from whichever is the lowest of the parts of your grade. And by that, I mean either the homework or one of the exams or the final, whatever that is. And I can't do that sort of tweak until we're all done. So in the back of your mind, you can just kind of keep in mind that your actual grade is probably a couple percent higher than what it actually says in there. It just isn't saying it now. So just keep that in mind a little bit. We do have another exam on May 1st, which is, gosh, it's already 2 weeks from now. I know, some time just flies when you're having fun, right? There is a resources folder. So far, all I have in there is just the sample exam and the solutions to it. I'm gonna make a review packet for you. Probably I'll get it in there this week and let you start looking at that. As always, I will be planning to do some review sessions before that exam. Again, it's on a Thursday. So I'll probably do review sessions early in the week, and then we'll take that third midterm, which is fairly close to the end of the semester at that point. That's kind of where we're at. Now I can give you briefly a little bit of the bad news. It's mostly been good news. I was looking back at all the homework assignments that I have for this class, and you may not realize this or not, we've been doing about one per week. Well, that would only add up to 15 homeworks because that's 15 weeks in the semester. I have 17 homeworks that covering the material. So I'm realizing that at this pace, we're not gonna get them all done. So let me just tell you where we're at with homework. We have one that's due tonight. Number 12 is due tonight. I sent out a bunch of hints to hopefully help you with that homework. If you have more questions on it, feel free to drop by my office hours this evening. I would recommend coming on the early side. Again, I'm not feeling 100%. If I have to go home and go to bed at 10 p.m., so be it. So I would try to catch me on the early side with any questions on the homework. The next assignment, I was looking at the assignment itself. there's quite a few problems on the next assignment, but I looked at all my solutions to them. They're all very short. They are mostly applications of the mean value theorem. And my entire typed up solutions to them are about half as long as the one for the current assignment. They're only like a couple of pages long. So I am gonna try to accelerate a little bit here, guys. And we're gonna have this one due on Saturday. I know that it might be a little bit of a short timeline, but I'm going to have some extra office hour. So I have my office hours today and Thursday. Friday and Saturday, I'll have some extra office hours. I'll send those out to you. I'm not going anywhere this weekend, so I should be around. And like I said, I do think this will go quickly. I do think it looks like as big of an assignment as always, but it's actually got some pretty short problems on it. That'll help us to kind of pick up the pace a little bit. Otherwise, we're gonna run out of time. We have too many problems to do at the end with not enough time to do them. So that's gonna be my game plan for the rest of this week. All right. So that's kind of where we're at for now. Anybody have any questions so far? Again, I appreciate so much your patience with me last week in Zoom. We talked about some applications of derivatives on on Thursday last week, and we're going to continue to build off of that today a little bit further. On Thursday last week, we talked about these two very closely related results. They're cousins of one another. We actually used Rolle's theorem to prove the mean value theorem, but then when you read the mean value theorem, you realize that Rolle's theorem is kind of like a special case of the mean value theorem. So you could actually prove, starting from here, you could prove this, or starting from here, you could prove this. It actually works both ways. And in that sense, they're kind of equivalent to each other. The Rolle's theorem, and I've got a picture that kind of gives you the intuition for both of these. Rolle's theorem just says, look, if your function is continuous on a closed interval and differentiable on the open interval, then as long as the endpoints are both zero, then somewhere in the middle, the derivative is zero. So there exists a C such that f prime of C is zero. Right. And then on the second one, yes, I forgot to label this as also f of x. The mean value theorem is probably the more famous result, the more broadly applicable result. Has the exact same assumptions. F is continuous on the closed interval AB, differentiable on the open interval AB. Then there exists, so this time we don't have any information about f of A or f of B, but regardless, there will exist a point C in the open interval, just like there was up here, such that f prime of C is equal to f of B minus f of A over B minus A. And that just means that the slope of the line that connects A f of A to B f of B has to agree with the actual tangent line slope at some point C. Okay, and it could be more than one value of C. We don't know that, but there has to exist at least one value of C in both of these theorems that satisfies the conclusion. Okay. Also, these theorems don't tell us where C is, other than it's in the open interval AB. It does not give us a construction of where the point C is or what it is. So this is just an existence result. There exists a C such that blah, 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 that f prime of C is equal to something. Are you guys following this so far? Is my voice coming through okay? Yeah. Okay, just trying to make sure. You guys are the lucky ones. I don't know how I'm gonna be by tonight. By 8 o'clock tonight could be a little rough, but we'll see. So I want to continue building more and more conclusions now from the mean value theorem. So we're going to do a bunch of applications of this, starting with the following corollary. The nice thing about what we're going to do today, guys, is that very little of this is going to be surprising to you. Like, all of these results, I think, will seem pretty normal, pretty expected. Okay. For corollary 5.2, I am going to start again with exactly the same assumptions. Let f be continuous on the closed interval AB and differentiable on the open interval AB. So once again, all of the same assumptions that we have for both Rolle's theorem and the mean value theorem. And now, if you're ready for this, I'm gonna give you 5, except I forgot one thing here. I'm gonna give you 5 conclusions, okay? Let me write them down. Actually, before I write them down, I'm so sorry, can I put a little recall over here? This is something I wrote down a definition a few weeks ago. This is not from last Thursday, it's just from a few weeks ago of what it means to say that a function is increasing or decreasing. So this is pretty simple. We say f is monotone increasing. So the function f is monotone if increasing if whenever x is less than y, then f of x is less than or equal to f of y. Okay, so that's monotone increasing, and then there's a similar notion. Also, f is strictly increasing. Squeeze this in right here. F is strictly increasing if whenever x is less than y, then f of x is strictly less than f of y. So these definitions would have been brought to you a few weeks ago, but we haven't used them lately, and I'm going to use them shortly. And I'm just going to say similar for decreasing. The only thing you have to change for decreasing is the direction of the inequality of the f of x and f of y. So if this was a greater than or equal to, or if this was a greater than, then your function would be monotone decreasing or strictly decreasing. Okay, so I meant to recall that before I actually stated this corollary over here. Are you guys with me so far? Yeah. Pretty reasonable, right? Yep, okay, so let's write down 5 results here. None of them are hard or surprising or anything. They're all going to be pretty straightforward. So here's the first one. If f prime of x is equal to 0 for all x in the open interval AB, then f is a constant function. So if the derivative is always 0, that just remember the derivative is really like the slope of the graph. If the slope is always 0, then your function is just a constant. Okay, pretty easy. Now let's do the next one. If the derivative of f is greater than or equal to 0 for all x in the open interval AB. So if the function has a derivative that's greater than or equal to 0, then f is monotone increasing. All right, so again, if the derivative is positive, then the function is monotone increasing. If we make that a strict inequality, so if we, for the third one, if we say that the derivative of f is strictly greater than 0 for all x in the open interval AB, then f is strictly increasing. All right, so that should be fine. And then I bet you know what 4 and 5 are. Same thing for decreasing, right? So number 4 would be if the derivative of f of x is less than 0 for all x in the open interval AB, then f is monotone decreasing. In that case, I'm sorry, that should be less than or equal to 0. So if f prime of x is less than or equal to 0, then f is monotone decreasing. And finally, number 5, if f prime of x is strictly less than 0 for all x in the open interval AB, then f is strictly decreasing. That's it. It's a whole lot of writing for a result that's pretty obvious, just from intuition, and also the proof is very short. So I'm going to write down the proof here. Nice thing today, most of these proofs are going to be pretty short. Okay, they're not too bad. So the proof, I do want to prove this rigorously. We're going to be using the mean value theorem to prove this. Let me get that circled so we can see it easily here. We're going to use this mean value theorem. And also, I'm going to start off, before I go into parts 1 through 5, I'm going to start with just a general setup of this. What I have to prove in all 5 cases is that f is whatever, increasing or decreasing. In other words, this definition here. Right, I'm going to be proving one of these things about f, whether it's monotone increasing, strictly increasing, monotone decreasing, or strictly decreasing, right? And in order to prove that, according to this definition, I have to have an x less than y. Okay, so I'm going to start this proof by fixing 2 numbers x and y that are in the interval AB with, and we may as well, without loss of generality, just assume that x is less than y. Now, you might be tempted to apply the mean value theorem to the closed interval AB. But actually, what I'm ultimately going to be wanting to compare is f of x with f of y. And so if I'm using the mean value theorem and I want to figure out a relationship between f of x and f of y, then I would not want to use the mean value theorem on the interval AB. Rather, I would see this relationship between x and y here and use it to make an interval for myself. So I'm actually going to make the interval to be the closed interval from x to y, which is inside of the original closed interval AB, which means that all of my assumptions, the continuity, the differentiability, those things will certainly still be true within this smaller interval that's inside of the interval AB. Okay, so let's do that. So let's just say here we will apply the mean value theorem. You guys are welcome to abbreviate that MVT, the mean value theorem. So we can apply the mean value theorem on the closed interval AB to find a C in the open interval AB. Sorry, the open interval XY. I keep saying AB, I meant XY. I wrote it correctly, I said it wrong. We will apply the mean value theorem on the closed interval XY to find a C on the open interval XY with f prime of C equals f of y minus f of x over y minus x. So this is what I'm doing. I'm applying the mean value theorem, but not with the interval AB, rather the interval xy. So far, so good? Well, now guys, now I'm ready to just run through 1, 2, 3, 4, and 5. If we start with number 1, so if f prime of everything is always equal to 0, then f prime of c would be 0, right? And so therefore, this fraction would be 0, and so on. So let's just start into it now. So for item 1, still doing the proof. For item 1, we have f prime of c equals 0. So that means that f of y minus f of x over y minus x is equal to 0. And hence, f of x equals f of y. Well, that's a constant function. So if you take any 2 points in the closed interval and evaluate f on any 2 arbitrary points, and you're always getting the same thing, no matter what x and y are, right? So x and y are fixed, but they are arbitrary. So this is for any x and y in this interval, so thus f is a constant function. Right, so f will be a constant function in that case. Bring this over here. Okay, well, let's look at 2. For 2, what do we have this time? Well, this time we have that f prime of c is greater than or equal to 0. So f of y minus f of x all over y minus x, this time it will be greater than or equal to 0. And guys, the denominator is positive for sure because y is greater than x. So it really comes down to the numerator here. If the whole fraction is greater than or equal to 0, then the numerator has to be greater than or equal to 0. So I'll just say it this way, f of y minus f of x is greater than or equal to 0. And so f is monotone increasing. Make sense? Remember, monotone increasing just means that whenever x is less than y, f of x should be less than or equal to f of y, and that's exactly what we've produced right here. Right, so that's pretty much the whole thing. And guys, 3, 4, and 5, these remaining results is just exactly the same thing again. You just repeat the same exact process. You start off by saying what f prime of c is going to look like, compare it with this fraction. You know what that fraction looks like, so then you look at the numerator and you get the conclusion that you want. So I'll just note that parts 3, 4, and 5 are all similar. We won't write them all out. You can just kind of repeat that same process again. I did it 2 times for you, but the idea starts to become pretty familiar from there. Okay, any questions on that? Seems okay, all right. I should point out that the converses of these 5 statements are also true as long as the function is differentiable. So if I know that my function is constant, then the derivative will be 0. If I know that my function is monotone increasing, then the derivative will be greater than or equal to 0. So this actually works both ways as long as f is still differentiable, which is part of the assumption anyway. So it does work in both directions. Just as another comment to make, but that's not really part of the statement here. I guess I could write that as a quick remark, just so we have it in the notes here. So as long as f is differentiable on this open interval AB, the converses of 1 through 5 also hold. They also hold. We're not going to stop to prove those now, but there's nothing that should surprise you about that at all. Because remember, the derivative is really gives you an idea of the slope of the graph, and the slope is tied to whether the function's increasing or decreasing. So if we know that the function's either increasing or decreasing, then we're going to know that the slope is either positive or negative. Okay, this is all kind of stuff that you would have talked about in your introductory calculus classes as well, right? Does that make sense? Let me know if I'm going too fast, guys. Let me give you some more applications. This can be viewed as an application of the mean value theorem. I'd like to highlight a few more applications. So more applications of the mean value theorem. And so we'll do a few of these, and some of them are numbered in the book. So the first one is actually corollary 5.3. Whenever you see the word corollary, you're talking about something that follows from an earlier result. In this case, the earlier result is our mean value theorem here. And we're gonna get an application of it in this corollary. This is also a very easy result that I'm sure you will know. It starts off with the exact same assumptions again. Let f be continuous on the closed interval AB and differentiable on the open interval AB. Okay, so all of these results are sort of starting off with that as a baseline. So we have to make that assumption first and then go from there. If f prime of x is equal to g prime of x for all x in that open interval AB. So if two functions have exactly the same derivative throughout the domain, in other words, they have exactly the same slope throughout the domain, then that actually will mean that the difference between these two functions is just a constant, right? They differ by a constant. So then there exists some number c, I'll just say c is some real number. There exists a constant number c such that f of x is equal to g of x plus c for all x in the open interval AB. This is just a well-known result that if you take any two antiderivatives for a function, so if these are really the same function, but you're taking antiderivatives of them, so you get f of x as being the antiderivative of f prime of x, and then g of x is the antiderivative of g prime of x, then they always differ by just a plus c. That's why when you evaluate indefinite integrals, they always make you put this plus c on the end of those antiderivatives, right? This is really where that comes from. And the proof of this is super easy. Okay, the proof here is super easy. So here it is, guys. For all x in the open interval AB, what we know is that f minus g prime of x is equal to 0. So if you subtract, well here, let me just add one more step. This is just f prime of x minus g prime of x, which is 0. And so I have a function whose derivative was equal to 0 for all x in the open interval. So if we come back to number 1 up here, if we have a function whose derivative is equal to 0 throughout the open interval, then it's a constant function. Okay, so by part 1, so by corollary 5.2, part 1, f minus g is a constant function. All right, so in other words, I could write that as f minus g of x is equal to c for some real number c. And now we just have to rearrange it to get the final conclusion. So then f of x is equal to g of x plus c, which is exactly what we wanted to prove here. Okay, back over here. Does that proof look okay to everybody? Pretty short and sweet, nothing too terrible about that. I hate to erase the mean value here. Keep using it. I can probably get one more result in before I have to erase it, because these results are short. This next one, if everybody's good with the antiderivative corollary there, the next one is something you've been probably wondering, where has it been? Why has he not talked about this yet? So I'm finally in a position to do that, which is a connection between derivatives and uniform continuity. Okay, so I'm going to give you another result here. This is going to be number 2. in my list of more applications of the MVT. This one is corollary 5.4, which we're gonna put right here. And what it says, guys, is that if F has a bounded derivative on any interval I. So in this case, it doesn't need to be set up to be an open interval or a closed interval. We can just talk about any kind of interval. It could be half open. It could go off to infinity on one side. But if F has a bounded derivative on any interval, then guess what? Then F is uniformly continuous on I. So if you have a function that's differentiable, and if that derivative function is a bounded function, meaning that the absolute value of f prime of x is less than or equal to some fixed bound, then your function is uniformly continuous. You can just state that immediately. Right? It will make your life, this one's going to come up. You're going to use this to do a problem that might normally take 5 or 10 minutes of epsilon delta work to prove uniform continuity. Instead of that, if you can take the derivative and just show that it's bounded, hey, you can use this corollary and you'll know already that you have a uniformly continuous function. So I need to do the proof of this, and I think I might want just a little bit more room. Let me come over here. It's not too long, but I don't want to squeeze it in too tight here. We'll keep our mean value theorem sort of on the board for a few more minutes. Okay, let's see what we can do for the proof of this corollary 5.4. Okay, so the assumption is that f has a bounded derivative on I. So let's assume that the absolute value of f prime of x, that's the derivative of f, and let's assume that that's bounded above by some maximum value, capital M, for all x in I. Maybe I should say, let's assume, sorry, I'm going to squeeze this in here. There exists an M greater than 0 such that, get my words inserted nicely for you there. So assume there exists a positive real number such that the derivative of f is bounded by that number M. Right, guys? So when you think about examples of functions that have not been uniformly continuous, most of those functions have derivatives that are not bounded. For example, so I'm just going to scribble here for a second. You're doing this one in the homework for tonight. X cubed is not uniformly continuous on the real number line. Well, if you take the derivative of x cubed, 3x squared, that is not bounded on R. If I allow x to be any real number, this could be as big as I want. There's no M for this that we could find, right? Another good example would be sine of 1 over x. That one's not uniformly continuous on R either, or even on just any interval that has 0 as an accumulation point, because the graph of this, you might remember, it looks kind of like this kind of wiggly thing. That derivative, the slope of that graph near the y-axis can be made as big as you want. It's not bounded. So that derivative is not bounded. So this function does not have a bounded derivative, and sure enough, it's not uniformly continuous on a domain that includes 0, or which is, I shouldn't say includes 0, but like the open interval 0 to 1, for example. And that's also a homework problem. I think as well. So anyway, a couple examples from the homework. Neither one of them has a bounded derivative. And that makes sense because if f has a bounded derivative, it's going to be uniformly continuous. Okay, getting back to the proof. I wrote down what it means to say that f has a bounded derivative on I. There exists some fixed positive value of m such that the absolute value of the derivative is less than or equal to m. And now I'm going to prove that such a function is uniformly continuous on I from the definition. Definition of uniform continuity is an epsilon delta definition. So you won't be surprised. I'm going to start off with my rubber stamp here. Let epsilon greater than 0 be given. Normally at this moment is where I go to my scratch work to solve for delta. However, for this proof, I'm just going to spill the beans and tell you what delta is going to be. I'm going to write it down and then we will check that it will work, okay? And it is simply going to be epsilon over m. And I point out that that is also positive because both m and epsilon are greater than 0. So that's my delta. And now what do I have to prove? I have to prove that if I take 2 points in I, such that absolute x minus y is less than delta, then absolute f of x minus f of y should be less than epsilon. Hopefully you guys have been continuing to rehearse your definitions a little bit here. But now I'm going to do that. I'm going to assume x and y are elements of my domain. In this case, I think in the original definition we used D for the domain, but in this case we're looking at an interval specifically. And without loss of generality, I'm just going to assume here that x is less than y. Okay. Such that absolute x minus y is less than delta. So I'm going to assume that I have 2 points whose difference is less than delta. And we can assume that x is less than y if we want, or y is less than x, it doesn't matter which one. That there's actually a reason that I'm making that assumption here. Like normally I don't do this part. Right? Normally when I'm checking uniform continuity and I have my delta, I just say assume this, right? Assume absolute x minus y is less than delta. So you might wonder, well, why am I assuming one of them is less than the other? It's because I actually want to make an interval that I can then apply my mean value theorem to. Okay, so anytime you see one number less than another number, you can always turn that into an interval and then apply your mean value theorem on that interval. It's kind of a neat strategy here. So that's exactly what we're going to do. So apply the mean value theorem on the interval that goes from x to y. And in doing that, what will happen is we will find, so to find a C in between x and y, so in the open interval x and y, with f prime of c equals, and I'm going to make a fraction out of this, it's going to be f of y minus f of x all over y minus x. Okay. So then the question becomes, what can you tell me about absolute f of x minus f of y? At the end of this proof, I need this difference to be less than epsilon. Okay, I didn't recap the definition of uniform continuity here. Hopefully I'm not in bad shape because of that. The definition of uniform continuity is that for all epsilon, there exists a delta such that if absolute x minus y is less than delta, then absolute f of x minus f of y is less than epsilon. Let's just see what this is. I'm gonna rewrite this equation as f prime of c times y minus x, and of course I've got absolute value bars around everything. So I'm just taking this fraction from the previous line and solving it for the numerator and putting absolute value bars around everything. But you guys all see that we're in good shape here? F prime of everything in I is always less than or equal to m. And actually, I'm going to make this a less than because the absolute value of y minus x is less than delta. But delta is epsilon over m, so that becomes epsilon. And so that finishes off your proof. Pretty nice. So far, so good? Questions? So this is a little bit of a fish out of water. This is not the section about uniform continuity. But here's this result kind of out of the blue that relates derivatives with uniform continuity. And I don't want you to lose track of this one since it's kind of in the wrong section. This gets used a lot. Let's just do an example of this result before we go any further. A quick example maybe to illustrate corollary 5.4. Let's just take f of x to be the sine of x. And let's just take the interval I to be the entire real number line. So we take the entire real number line, we'll just take sine of x, right? Well, then what we know is that the derivative of sine, we did this last week in Zoom, right? The derivative of sine is cosine. And so if I put absolute value bars around that, put absolute value bars on everything, what can you tell me about the absolute value of the cosine of x? One more time. It's between 0 and 1, right? It's definitely less than 1. It's bounded by a bound of, well, I can put less than or equal to 1. But I could take an m value of 1 here, and so this function has a bounded derivative, right? And that's for all x in R. This is for all real numbers. Okay, great. So f has a bounded derivative on R. And so by corollary 5.4, f is uniformly continuous on R. So the sine of x is uniformly continuous on the real numbers. It has a bounded derivative. This would be hard to prove directly. It would be hard to prove directly that the sine of x is uniformly continuous because you'd have to look at absolute value of sine of x minus sine of y and try to say something about it. And it's a little bit hard when you're dealing with a trig function to get much mileage out of that. But here, we're getting the conclusion through the use of that corollary. Okay. Maybe one more example. Let's do one more to practice a little bit further. Isn't there a problem on today's homework? I think it's one of the first ones. F of x equals 1 over x squared. And you're supposed to prove something about this being uniformly continuous on some domain. Let's take the interval I to be some domain from C to infinity.
Yeah.
Where C is greater than 0. Does that look familiar?
Yeah.
Yeah. So there's an example of a problem, and I think the problem is asking you to prove that it's uniformly continuous on this domain.
Yeah.
Okay, so most of you have already done this problem. If not, you're gonna hate me now, because I'm gonna prove it in one line. All I'm gonna do is take the derivative of this and make sure it's bounded, and then I'm gonna know it's uniformly continuous on that interval, right? So this is the beautiful thing about it, right? So let's just check it out. So then the absolute value of the derivative of this, let's just see if we can calculate it. That would be the absolute value of, if we just take the derivative using the power rule, we should get -2 over x cubed. So I'll put absolute value bars on that. And I can get rid of the absolute value bars by moving the minus sign, or getting rid of the minus sign, so it's just 2 over x cubed. Keep in mind, guys, c is greater than 0, and so your x's are going to be greater than c, which is greater than 0. So you don't have to worry about negative numbers here at all. Everything is positive. But this guy, right, this guy will be less than or equal to 2 over c cubed. This is since x lives in this interval from c to infinity. You see, you can't declare 2 over x cubed to be m, because 2 over x cubed is not a constant. It depends on x. But if you replace that denominator with a smaller denominator, namely c, now you have a constant. 2 over c cubed is a constant value. You can use that like your m. And so that means that, you've got your bounded derivative again. And so the corollary allows you to conclude that f is uniformly continuous. So thus, f is uniformly continuous on this domain from c to infinity by corollary 5.4. Now, of course, that only works if c is greater than 0. If you try to change this interval in some way, well, of course, you could not include 0 anyway, because the function isn't even defined at 0. If you tried to define it at 0, though, let's say you made a piecewise function and you said, I'm going to let f of x equal 1 over x squared, except at 0, and f of 0 equals 0, or something like that. You could do that to sort of fix the problem at 0 here. However, you would not be able to prove that this is uniformly continuous on 0 to infinity, right? Because you can see here that your derivative is not bounded if you allow 0 to be part of that interval I. So this is a situation, here's 0 and c is over here, and there is actually space in between 0 and c. And then, of course, all of the x's that you're looking at are even further over to the right. So that's kind of the way that those variables are related to each other. Okay? Right, kind of following this? How's that Phil's coffee? Pretty good. It is funny. Some of you probably have been in my office enough to know that I'm kind of a soda addict. I drink a lot of soda, except it's diet. It's like a Coke Zero type of thing. I can't stand alcohol. I never had a drop of it in my life. And I also can't stand coffee. I went to a meeting Sunday. I had to go out to Channel Islands to go to a meeting. They usually have breakfast for us, so they have bagels and stuff. And they come in almost every time I've gone to one of these meetings. I have to do it like 4 times a year because I'm on this board of directors for this regional conference that we host in this area. And we always have these board meetings, and they always come in with juice and coffee and tea and water and everything else. The guy comes in with just one thing of coffee. That was the only thing they had to drink. And I was really thirsty. I was like, I guess I'm gonna drink coffee this morning. And I tried it and I just hated it. Oh my gosh, I just don't like coffee. You're having coffee too. Yeah, I wish I liked it better because it's so easy to get it, but I'm not a coffee person either. I just don't like the taste of it. I love the smell of it, but I just don't like the taste of coffee.
Because of the caffeine?
No, I don't think so. Like with soda, if I drink caffeine or caffeine free, it makes no difference to me. I'm pretty wired up anyway, whether there's caffeine or not. I don't think it's about the caffeine. I just have not acquired that taste for it. Both of my parents love coffee. Every morning they're brewing the coffee. It smells up the whole house. I love the smell. I can't stand the taste of it. Anyway, what was I talking about? I was doing some consequences of the mean value theorem. I want to do one more before we take a break today. And then we'll take a 10-minute break. The third application. So guys, have I impressed you on this one?
Yeah.
This is a big deal. Pay attention to it. We've got 2 examples right here of how we can use it. You're gonna see more examples in the future as well. So definitely worth paying attention to. So let's do one more. The third one is not a particular result out of the book, but rather a whole sort of family of examples. I'm gonna call this little subsection inequalities. And we can use the mean value theorem to establish these. So we can try to use the mean value theorem to establish some of these inequalities. And I think the best way to illustrate this is with I'm gonna jump straight into the examples this time, and you will see these on the homework. And they kind of stand out. It's like, well, you're being asked to prove some inequality. So here would be an example. Prove that for all x in the real numbers, e to the x is greater than or equal to 1 plus x. Okay. So we'll do this as a solution here. I'm going to prove this for positive x's, and then 0, of course, it has to be true for 0, and then negative x's, and so on, right? So I can't just do this in one swipe with all x's represented at the same time. But what I could do is I could sort of do case 1, x equals 0. Now, in the case when x is equal to 0, what do we have here? E to the 0 greater than or equal to 1 plus 0. Is that true?
Yes.
Sure is. They're both equal to 1, right? So we'll check that one off. So let's go to case 2. Case 2 is going to be x greater than 0. Now, the trick here, this is a little subtle, but you guys will get good at this if you just practice it a few times with me. Because I've said x is greater than 0, I have actually inherently made an interval there. It's the if I want to apply the mean value theorem, I have to have an interval in my hands. And I now have one that goes from 0 to x. And I'm going to make that as my interval. So let's consider f of x equals, I'm going to use e to the x on the interval from 0 to x. So I'm gonna just call this function e to the x, I'm just gonna call that f of x here. And I'm just gonna consider this interval. Now, to use the mean value theorem, which is actually still in the box here, we will need to know the derivative of f. Of course, the exponential function is continuous everywhere, and it is its own derivative, in fact. So this thing is well known to be continuous and differentiable. So I'll just say then f prime of x is also e to the x. Okay, so we do know that. And so let's apply the mean value theorem on that closed interval 0x to find, well, what we always call C. C is going to be in the open interval from 0 to x, such that, or with, I'll just say with, f prime of C equals, well, this should be f of x minus f of 0 all over x minus 0. This is just my usual fraction that we have in the mean value theorem. And let's plug everything in. F of x is just e to the x. F of 0 is e to the 0, which is 1. And then in the denominator, we just have an x here. Okay, and f prime of c is just e to the c. So we can say e to the c is equal to e to the x minus 1 all over x. Now, guys, what I'm trying to do is prove that e to the x is greater than or equal to something. So you know what I should do now? I should try to isolate e to the x so I can see what I can compare it with, right? So let's go ahead and solve this for e to the x. It's going to be x times e to the c plus 1, I believe. I did that correctly? But notice, guys, that c is greater than 0 but less than x, right? This c value is somewhere between 0 and x, which means that e to the c is at least what? 1, right? Because e to the 0, if c was equal to 0, that's the smallest value it could be. E to the 0 would be 1. So this is actually greater than x plus 1. Since e to the c is greater than e to the 0, which is equal to 1. Yeah. So in this case, in case 2, when x is greater than 0, we actually prove that e to the x is greater than x plus 1. The ultimate problem has a weak greater than or equal to here, but the equal to part really goes to case 1. And now in case 2, we actually get a strict greater than inequality there. Okay, and then for case 3, this is when x is less than 0. I am not going to do this one. I'm just going to say similar to case 2. With the interval, this time your interval would go from x to 0. So you have to tweak it a little bit, and instead of the interval being from 0 to x, now the interval is between x and 0. So you notice that when I'm trying to apply this mean value theorem, I have to sort of have an interval. I have to know which number is smaller than the other one, right? Like here, I had to assume that x was less than y in order to actually make an interval. So that's just a little extra step we have to do sometimes on these. But not too crazy. So far, so good? Questions? Do I seem like I'm like not myself today? I seem okay. I think math has that effect on me. It's like my medication. It just, even if I'm sick, I still get excited about it. So I come in here and like, oh, forgot that anything was wrong. All right, let's do one more example of inequalities here, and then we'll take a break. You're gonna have a couple of these on the homework. I know one of them involves the natural log function. You're allowed, by the way, on that homework, this is for Saturday's homework. You guys are more than welcome to just use the fact that the derivative of the ln of x is 1 over x. I think that will come up on the next homework assignment. We didn't prove that or anything, but you could certainly, well, you proved it in your basic calculus class, probably. Maybe 3 years ago, whenever you took it, they probably proved that, so we'll just call that good. Anyway, let's do one more example here, just to make sure everybody's feeling good about this. Prove that for all h greater than 0, the square root of 1 plus h is less than 1 plus h over 2. Right. So does anybody want to help me out? Since we've done one already, maybe you can help me how I might set this one up. So on that problem, we used cases because we didn't know anything about x. So in this case, it was for all x in R, and x could be 0, or it could be positive, or it could be negative. In this problem, are we looking at the entire real numbers? Just the positives. So actually, in that sense, we only really have one case here. So we're in the case where h is greater than 0. But what do you suppose I might do with that? Louise? Make the interval from 0 to h, exactly right. So let's consider the closed interval from 0 to h. I'm trying to set myself up to use the mean value theorem. Okay, now to use the mean value theorem, I also have to have a function in my hands. So I need some kind of an f of x. Anybody want to help me with what f of x should be? Square root of, well, let's call it 1 plus x. But yeah, so we could just use the square root of 1 plus x, which is certainly defined throughout this interval. Okay, so without further ado, let's take the derivative of this. And I'm doing that because the mean value theorem will require us to look at the derivative of the function. So f prime of x, we have to use the chain rule here. So the 1/2 for the radical comes down, leaving me with 1 plus x to the negative 1/2. And then the derivative of 1 plus x is just 1. So I don't have anything else to write down. And so this is 1/2 times the square root of 1 plus x. I don't like negative exponents. I never did. So I'll just use a radical underneath this fraction here. Okay, and now without thinking too hard, let's just go right into the mean value theorem. I have my function. By the way, the only place where this thing would be a problem is if x was -1 or less, then we would have difficulties with these radicals and denominators. But we're not working with values that are to the left of -1. Everything we're going to consider is on the interval from 0 to some positive number h. So this is all good to go. We can apply the mean value theorem to find a c in that open interval from 0 to h with f prime of c equal to f of h minus f of 0 all over h minus 0. Okay. And let's clean this up on both sides. On the left side, that would be f prime of c would be 1/2 times the square root of 1 plus c. And on the right side, let's see, f of h would be the square root of 1 plus h minus f of 0, which is actually just equal to 1. And the denominator would just be h itself. Okay. And just like the last example, my goal here is to prove something about the square root of 1 plus h. This is what we're proving. And I see the square root of 1 plus h now in my calculation. So I can try to focus on that and isolate the square root of 1 plus h. Okay, so just do a little algebra with me and we should be in pretty good shape. The square root of 1 plus h, if we solve for it, is going to be 1 plus h over 2 radical 1 plus c. So if we just cross multiply it and add 1 to both sides, I guess, that's what we should have if I did it right. Just stop me if I made any mistake. Hopefully so far so good. And now this is what we have, and this is what we want. So we have to compare, and of course this is an equal sign. This should be a less than. So can we go from what we have here to what the right-hand side is supposed to be? It's already looking almost good to go, right? We have 1 plus h over 2 here. And I'd love to just say that. Now, is that true? Is that true? Let's see, what's the difference between these two? Well, there's an extra denominator here. This extra denominator, let's see, c is at least 0. So this denominator here under that radical is at least 1. That's making this denominator bigger. So if I got rid of that, if I removed that radical 1 plus c, what's going to happen? I'm actually going to make the h over 2 standing alone bigger. And so this is definitely true. Okay, so I'll just say since the square root of 1 plus c is at least 1. So that denominator is making the left side actually a smaller total sum than the right side. So I could go on, there's so many applications of the mean value theorem, that, we could keep going. What we're gonna wanna do next is try to figure out how we could maybe improve on the mean value theorem by not being constrained to only looking at the first derivative. Remember, last week I talked about the second derivatives, third derivatives, fourth derivatives, and using those higher derivatives, we can actually get better approximations of our functions. Like here, we're approximating e to the x with 1 plus x. But you guys probably know that there's a Taylor expansion for e to the x that has a whole lot more terms than just 1 and x. There's actually an infinite series that represents e to the x. So the question would be, could we do that by just expanding the mean value theorem a little bit? So I'm gonna talk about that after a little bit, in a little bit. Let's take a 10-minute break though, give myself especially a chance to rest my voice and give you guys a chance to stretch your legs a little bit. And we'll be back in 10 minutes. Robert. Right here. Clayton. And Cozy. This is the only class I'm taking. Yeah.
I believe in you. Just make sure you do the homework.
Yeah.
Make sure you do the homework.
Yeah.
And just study them.
Yeah.
Study for the samples, the exams.
But yeah, I did better than last.
It's good.
Yeah.
So what do you get last time?
I got
for the exam.
50.
What do you get on the exam? This one or the last one? This one. Dang, you beat me. I got it too, so I'm feeling proud of myself.
What the heck? I thought that could have 6, 7, 65. I thought that was
How
7.
much you gonna take more portion?
That's 28.
How many?
Yeah. So you told me that. But
Oh,
just,
well, I was like, the goal is to get.
yeah, my goal was 7.
Wait, 28 of how much?
20 out.
You said 20.
No, 28.
Oh, it's 28.
Because I took a number 1. That's what hope. Yeah, so I just took it, even though I was confused.
And I'm not risky.
Yeah. Still a lot of like mistake, like. I use like 580 or something. Place I just use it without any juice. But you just still get some part of it. That was good.
I'm looking, so start getting mad.
How's it working?
It was good.
Yeah?
Yeah.
You met the coach?
Went to, I mean, one of the coaches already, but got to meet the rest of the staff and then went to their practice for stuff, so
Oh.
that was good.
Don't live.
No, I'm gonna be at rest.
Don't you have 4 years of eligibility?
Eligibility.
You can really change it.
We,
For
for like, if
soccer.
you go to like JUCO or,
Mhm.
yeah,
Yeah, all 4 years.
yeah, you get all those back. But yeah, I was the first class that didn't have like a COVID year. And I never like redshirted or anything, so.
You paid, Francis? Once you get paid. Also, are you eligible in state, as you say, or?
I literally went to the DMV yesterday.
Oh, or you're just waiting?
Yeah, but I'll get my license, go to registration,
Oh.
and because I did the science thing. That's
Oh,
pretty good. So
that's nice.
the grad assistant is like half the tuition,
Oh, the signs.
so. That should be helpful.
Not doing extra work, just the. That's good.
So, I'm all for like full-time travel too, just kind of rely on definitely will have to miss. But, it's
Yeah.
essentially, so.
Right.
What did you decide on?
I got elected last week from Brooklyn. This accepted. Still waiting, but I'm still
Nice.
so.
That's exciting.
Dr. Ed,
Yes.
can you give me a job in data science?
Yeah.
Okay.
So
I'm a theoretical mathematician.
Yeah, I gotta talk to the stats professor.
I think so. Yeah, it's a hot topic right now, I do know that.
Security AI is gonna take over.
Are you?
No.
You know, I had to fill out, I don't know what it is, I keep getting these surveys to fill out. Like, are you worried about AI? Do you plan to use AI? Are you incorporating it into your teaching? Are you incorporating it into your everything, your whole life? And it's like, they really wanna know how we all feel about this. I think AI gets a lot of stuff wrong.
Does.
You know, and I'm not even really trying to ask AI, it just, like, if I search for something, it just pulls it up.
Yeah, review.
And I was like, who asked for your opinion? The thing I love is that nothing in this book, nothing in this book is affected by AI. The math is the math, it's gonna stay the same, so this book can survive forever.
But I guess.
Yeah, I think there's a using
I don't
like
know.
private API.
In whatever context, you could just like tell somebody the answer and they wouldn't want you to explain why you did that.
Now, the one thing that I was worried about, because I'm a theoretical mathematician, and specifically I'm an algebraist, which means I have an interest in number theory. I was worried about quantum computing, because that could put all the, you know, like the internet security stuff, you're protecting your personal information online. That stuff is protected by a system that, as of now, is very safe because there's no way to factor large numbers quickly. But if quantum computers get brought up online, which they do exist, but that, at least as of now, they're not an immediate threat, but those could pose a risk to the internet. I always have this fear that someday I'm gonna wake up and like, you know, the internet will have been taken over by aliens or something, and suddenly nobody will be able to talk to anybody or do anything. Cause we've become so dependent on it, you know, so.
There's a movie about that. This one on Netflix. It was called.
Yeah, I don't doubt it. It would make a good film, I just wish it was only in science fiction.
You have a lot of pure prediction. You don't even know soon. You're building your own network.
That's true.
Yeah, for like a lot of things, just now. somebody to explain.
Did your interview go well?
Funny thing, I thought it was on, Thursday, it was actually on Tuesday, so I didn't go.
Oh, you missed it?
Yeah.
Oh, no. So that went down the drain?
No, just 6 weeks pushed back.
Oh, push back over the summer?
Yeah,
Okay.
I don't know, like 50-50. Want to do that or data science?
Uh-huh.
I'm still applying like internships.
Well, those are real close.
I know, right?
I'm being sarcastic.
Yeah, I know.
This out. We're gonna get to this in a few minutes. Just a little pop quiz. Only worth 20% of your grades, don't worry. We're not gonna do that group work quite yet, but I just figure I'll pass it out now. All right, guys, I think everybody might be back at this point who's here today, so I think I'll start up again. We're just gonna talk a little bit more here. And then I'm gonna save some time at the end of class for you to work on that group work. You didn't get the group work yet.
Oh, no.
It's okay. Um, I want to briefly talk about the start of the next section, and I'm actually gonna end up asking you to watch a video and take some notes on it. Turns out, I don't know what it is, but I made a YouTube video about Taylor's theorem, and it might be my most popular video on the internet. I don't know. I've like suddenly, like everybody, if you search for Taylor's theorem, you find me like I'm some kind of expert on Taylor's theorem, and I didn't quite understand why it got so popular. But anyway, I figure, well, you at least you guys should watch it too then, since 60,000 other people have. And maybe you'll make some sense out of it. So that'll be the proof of Taylor's theorem, but I'm going to lead up to it. And that's what this next little section is about, 5.3. Taylor's theorem. And this is probably the last section we're going to cover about derivatives. I think I'm going to end up skipping L'Hopital's rule in this class, just because you do a lot of that in your basic calculus courses, and I want to move on to integration, which is really my favorite thing. But Taylor's theorem is, the idea of it is to take any function that has derivatives that you can compute, so differentiable up to a certain number of times, and approximate your function as a polynomial. And the coefficients of that polynomial will require us to know what those higher derivatives of f are. Guys, what could be nicer than a polynomial? Polynomials are differentiable. You can take derivatives of them forever. They're easy to take derivatives of, easy to evaluate, easy to draw graphs of, right? We have a lot of good experience with polynomials. So that's going to be the idea. Taylor's theorem specifically measures or gives us a way of measuring the error in using a polynomial to approximate a function at a certain point. So that's kind of just a quick idea. Maybe I'll just write this down. A quick idea behind what we're going to do here is, given a function. I'll call it f, like always, from D to R. And if we take some point, I'll call it x naught that's in the domain. So given a function f and some point in the domain, we wish to approximate f by a polynomial. And that approximation is not going to be valid throughout the entire real number line. But it hopefully will be a good approximation near x naught, right? By a polynomial, let's just say in the vicinity, I know that's a little bit of a vague term, but in the vicinity of x naught. The farther we go away from x naught, the weaker that approximation will be, right? So that's the idea. This theorem, by the way, was proven in 1715. So this goes back 300 plus years. There was a bit of controversy over who actually discovered it. So Taylor obviously is in the mix, but there were some other people who also published results like this, and it's a little bit unclear what the timeline of that was. But when you see the theorem, you'll recognize that it's essentially a generalization of the mean value theorem, which we've already been talking quite a bit about, okay? Polynomials have the advantage, I've already kind of mentioned this, polynomials are quote unquote nice. So what I mean by nice is easy to evaluate, graph, differentiate, integrate, etc. Right? So lots of other things that you would have seen in other classes. You know, for example, you guys have seen examples of functions that are not integrable. In your basic calculus classes, they probably showed you some examples of functions, like you cannot evaluate the integral of e to the negative x squared, for example. This is impossible. So what can you do? Instead of that, you can approximate e to the negative x squared by a polynomial, and polynomials are easy to integrate. So that's the idea behind what we're going to do here. Okay, so let me talk about what this Taylor polynomial is. I'm going to make a definition here. Is everybody okay so far? Any questions? Okay, let's just make a definition here. I'm going to call this the nth Taylor polynomial. So n is some number, and I'll explain in a minute what that's talking about. The nth Taylor polynomial, I'm going to be denoting this as p sub n of x, centered at x equals x naught. So x naught is this fixed point in the domain, is the following polynomial. Okay, so I'm going to write it here. Give yourself plenty of room to, this is one you're going to want to memorize. Give it a nice big box around it in a second. The thing about this polynomial is we want it to be a good approximation to f in the vicinity of x naught. So we want it to be having as many things in common with f as possible. So for example, if I plug x naught into the polynomial, I would hope that the answer that I would get would be the same as f of x naught. I would want the polynomial evaluated at x naught to agree with f at x naught. So I'm going to start with that, f of x naught. Okay, but more than that, if I stop right now, then what I've done is I've made a constant approximation. It's just a horizontal line because this is just a fixed number. But I want to do better than that. I also would like my Taylor polynomial to have the same slope as f at x naught. So in other words, if I was to take the derivative of whatever I'm putting here, I would like, and if I took that derivative and evaluated it at x naught, I would like the answer to be f prime of x naught, right? So we would need to add that as well, so this is going to be f prime of x naught times the quantity x minus x naught. Okay. So look, I'm still not done. But just, if you stop with me for a second, if you take the derivative of that thing, right, the derivative of a constant is 0. Here, I have x times some coefficient, so the derivative of this is just f prime of x naught. Okay, so Pn prime of x naught agrees with f prime of x naught. So far, the polynomial agrees with the function, the derivative of the polynomial agrees with the derivative of the function, and I would like that to be true for the second derivative as well. So I'm gonna do another term. This is probably gonna look a little bit familiar if you remember it from your calculus courses. We're going to have a 1/2 factorial times 2 derivatives of f evaluated at x naught times x minus x naught squared. Now again, if I stop here, if I plug in x naught everywhere I see an x, I get Pn of x naught equals f of x naught. Everything else becomes 0. If I take one derivative of the right-hand side, the first term goes away, the second term gives me the f prime of x naught, and the third term will go away also, because when you take one derivative of this, you'll still keep x minus x naught, like the 2 comes down, and you'll get x minus x naught, and when you plug in x naught for x, it becomes 0 as well. Okay, and then if you take 2 derivatives of the right-hand side, both of these first 2 terms get totally canceled out, and you'll just have this one, and the 2 comes down and cancels the 2 factorial, and you'll just get the second derivative of x naught. Is basically what's going to happen. So we're setting this up so that, so what I'm trying to say is, I'm not just pulling this out of the sky randomly. This definition, which I'm still not done on, I like to keep you on your edge of your seats for a minute, but where this is coming from is we're making this formula so that f and this polynomial have the same derivatives at x naught up through, well, n derivatives, right? So we go all the way, the dot 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 means I'm gonna go all the way up to 1/n factorial times n derivatives of f evaluated at x naught times the quantity x minus x naught to the n. Okay, so there you have it. That is the nth degree Taylor polynomial, Pn of x. So the larger n is, the more terms you have to write down, but also the better the approximation is that you're gonna get. So it's kind of, depends on how good of a quality of a approximation you want your polynomial to have to f. The bigger n is, the more derivatives of f agree with that approximation. Now, it kind of goes without saying, but I am gonna say it, that you can see that make a little remark here. I am using derivatives of f here. I didn't say anywhere on the board, oh, f has to be differentiable, but you can obviously see that that is assumed. So this assumes, this definition requires that f prime, f double prime, and dot 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 all the way up to n derivatives of f exists at the input value of x naught. You have to have all those derivatives, otherwise the right-hand side doesn't make sense. Yeah, so all of those derivatives must exist. And then the second remark is, it is easy to see. I'm not going to really do it, but I've kind of talked through it a little bit, but I'm just going to make it as a remark for now. It is easy to see that for all k less than or equal to n, if you take your Taylor polynomial and you take k derivatives of it and you evaluate that at x naught? So you take this Taylor polynomial that we just defined, you take k derivatives of it and you plug in x naught, it will agree with k derivatives of f at x naught. So the idea here is that the Taylor polynomial really is an approximation to f of x because it agrees with f of x all the way up through k derivatives. It's got the same value at x naught, the same slope at x naught, the same concavity at x naught, and so on. Third derivative, fourth derivative, all the way up through the nth derivative. They are all the same for both of those functions. So Pn of x is approximately f of x for x near x naught. For values of x that are near x naught, this polynomial should be a nice approximation. But the question, so far there's no theorem here. So far, all I've done is defined this Taylor polynomial, and we can do that, right? We can make that definition, but the problem with this is that when we make this polynomial approximation, there could be an error associated with that. And the question is sort of, what is that error going to be, right? So what is the error? The error in this approximation. That's kind of the $1 million question here. What is the error that would come up in using the Taylor polynomial to approximate our function? I'd like to use that polynomial as an approximation, but I have to know how good of an approximation is it? So what is the error? And when I say what is the error, I really mean what's like the worst case scenario? Like how far off could f of x be from Pn of x? It's obviously going to depend on how far x is away from x naught. It's probably going to depend on n. If I took a larger n value, then my approximation is probably better than it would have been with a smaller value. So there's some things that we might expect the answer to be based on, but this is answered. This question is answered by Taylor's theorem. So now I'm going to state Taylor's theorem. As I said, I'm going to ask you guys to watch a video to see the proof of this theorem. I'll probably have you take some notes and submit them for me. It's a little bit of an involved proof, but I try my best in the video. So anyway, this is in the book. This is 5.6. You're keeping track of the references for the book, theorem 5.6. So let's just state this here. Let f be a function from the closed interval from AB to R. So that's been pretty much everything today. I'm going to let n be some natural number. Again, we have an n value. And assume that f and f prime and f double prime and all the way up to f to the n derivatives, all of those various derivative functions that, well, obviously they have to exist, but I'm going to say more than that they are actually continuous on the same closed interval, AB. This takes a little bit to write down, by the way. Okay, so this is not a short theorem to write down. Just writing it down takes a little bit. So assume that all of these derivatives of f are continuous on AB, and it turns out that to actually address the error between the f of x and the Pn of x, we actually need to go up to the next derivative. So we're going to go all the way to the n plus first derivative. And the point we need here is that this exists on the open interval AB. So the previous derivatives, they all have to be continuous on the closed interval. The next derivative up needs to exist on the open interval. Okay, so we're gonna start off with that. Then we're going to let x naught be an element of the closed interval AB, but not, yeah, sorry, right, so just gonna pick some point in the closed interval, that's gonna be where we center. So we're going to center our polynomial approximation at x naught. Okay, that's the point that we're given. So then, for all x not equal to x naught in that same interval AB, so we take any other point in that same interval AB. So, yeah, here's just a picture of the interval. This isn't terribly illuminating, but you've got some x naught in that interval, and then you're gonna just look at x, which is just some other point in that interval as well. So for all x not equal to x naught, there exists a C between x and x naught. I should point out, I don't actually know which one of these is bigger. I don't know which of these is bigger. It just says for all x not equal to x naught. So x could be bigger than x naught or smaller than x naught. So I can't really write an interval here because I don't know, is it an interval from x to x naught or is it the interval from x naught to x? It would depend on which one is smaller and which one is bigger to write that interval. So that's why I'm writing it in words. There exists a C between x and x naught such that, and here's what we're gonna do, guys. We're gonna write f of x is equal to f of x naught plus f prime of x naught times x minus x naught plus the next term is f double prime of x naught over 2 factorial times x minus x naught squared and plus dot 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 plus n derivatives of f at x naught divided by n factorial times x minus x naught to the n. Now, I'm not done yet, but what I've written on the right-hand side of the equal sign is exactly just Pn of x again. It's the same exact thing. But what I'm gonna do now is, you notice I don't have an approximate here. I have an equal sign, which means I'm going to add one more term. And this last term that I'm about to write down is going to be the error term, right? So this is, so far, this much that I've written down so far is Pn of x. So we're comparing f of x with Pn of x, and we're wondering, what is the error in doing that? How close are they to each other? Well, the error is gonna be this term right here. It's actually got a name. It's called the remainder term. So I write Rn of x for this. This is often called the remainder. I'll just put in parentheses. You could think of it as the error term. So that's gonna be measuring the error. And what is this thing? Well, I have to write it down. N plus 1 derivatives of f, but not evaluated at x naught, rather evaluated at c. And then we will divide by n plus 1 factorial. And then we will have x minus x naught to the n plus 1 power. Can you guys all read that? It's a little bit small here. This is x minus x naught to the n plus 1 divided by n plus 1 factorial. The only difference here is that we didn't put an x naught here, we put c here. Is everybody with me? Now, here's the thing. We probably don't know what c is. Actually, if we knew what c was, this theorem doesn't tell us what c is. It just says there exists a c. If we could actually figure out what c was equal to, then we wouldn't need an approximation. We would have an exact formula for f of x. It's this polynomial plus something else that we would be explicitly able to find out. But see, I don't know what C is, all I know is it's between X and X naught. And what you're gonna have to do when you're applying this theorem is you're gonna have to say, well, what value of C between X and X naught would give me the biggest remainder, the biggest error term? And that would be like your upper bound for your error. I always like it when people will do an approximation and somebody will ask them, oh, what's the error in that approximation? If I knew exactly what the error was, then I could take that difference, add it to what my estimate was, and then come up with the exact right value, right? So we don't actually know what the remainder is. We can put a bound on it. We can say at worst, if we choose C to be, it's usually either X or X naught, if we choose C at the end point of our interval, we'll make this term the biggest it could possibly be, but we don't actually know what C is, so we can't say for sure that that's the error. In other words, it's not precisely the error. So anyway, I'll just make this as a quick remark here. The remark is that Rn of x, which is really just f of x minus Pn of x, measures the error in our approximation. It measures the error in our approximation. That's basically what's going to happen. Okay. But we would like this to be small. Generally, I'm not going to know explicitly what this is equal to for any particular value of x. But we would like to put a bound on it, right? So the goal here is to put an upper bound on the absolute value of Rn of x. Try to put a bound on that remainder term. Okay. One more remark and then I'm gonna be done for today. Like I said, the proof of this is a video for you guys to watch, which I will send to you. On Thursday, I'll do a couple applications of this and then we're gonna call it good. But quick remark here, if n is equal to 0, final little comment for today's notes. If n is equal to 0, then what does this theorem boil down to? So if n is equal to 0, then what we have on the left side is f of x. And what do we have on the right side? If n is 0, then we actually are stopping already with just the f of x term, f of x naught term. Okay, because this would be n equals 1, this would be n equals 2, this is n equals 3, this is n equals n, right? So n equals 0 would just stop at f of x naught. And what we would be left with then, we would be going straight to the remainder term. And what would the remainder term say? It would say n plus 1, that would be 1 derivatives of f at c, times x minus x naught to the first power divided by 1 factorial, that would be equal to that. What is this? Let me just solve this for f prime of c. If I solve this for f prime of c, does it look familiar? F of x minus f of x naught over x minus x naught. Say it again.
The mean value theorem.
This is just the mean value theorem again, right? Exactly. There exists a c such that f prime of c is equal to, this was f of b minus f of a over b minus a before, but now we're working with a new interval, which is just the interval between x and x naught. So let's just say, which is just the mean value theorem applied on x naught, or see, we don't know which one is bigger, so I'll write it both ways. It could be the interval from x to x naught, or it could be the interval from x naught to x. Yeah. Okay. Does this make sense? So then what we're trying to say here is that this theorem generalizes the mean value theorem. So in other words, so maybe I should add one more thing. So thus, Taylor's theorem with n equals 0 is literally the same. That's a bold equal sign. Mean value theorem. It's just the same thing as the mean value theorem. So if you just stop at n equals 0, you're talking about the mean value theorem. But this is generalizing it. We're doing approximations using higher and higher degree polynomials. The concept is pretty straightforward. Okay, so we've got one glaring detail missing, which is the proof of this thing. Other than that, well, I guess two glaring details. The second one being any applications of this result. But I don't really have time to do them today. I think I passed out this group work. Would you guys be responsible enough to come back with it in 48 hours? Or do I need to print these all out again on Thursday? I didn't quite get to it, so why don't we plan on doing this on Thursday? This is a pretty easy group work, just 2 questions, it wouldn't take us too long. But you know what, if there was ever a day that I thought I might want to quit 5 minutes early, it might be today. I just need to rest my voice as much as I can. Does that sound all right? Okay, I will let you go early and we will reconvene on office hours if you need any help with the homework, or Thursday. See you guys then.